Good morning and good evening, everyone. I'm Jianing Zhu, a PhD student from HKBU. Today, I'm going to host the 22nd TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our vulnerable guests and audience. The full name of Recon AIP is Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the Max AIP project. AIP Center conducts the Japan's leading AI research, which is handled by Professor Sugiyama. AIP aims to enhance AI fundamental research. And AIP encourages the collaborations with various researchers and engineers in related fields. Today, we are very excited to have Junyuan Hong, who will give us the talk named Efficient Split Mix Federated Learning for On-Demand and In-situ Customization. Junyuan is a PhD student in Computer Science and Engineering Department at Michigan State University, working with Professor Jiayu Zhou. His research interests are in federated learning and privacy-preserving learning. Prior to MSU, he received his master's and bachelor's degrees in computer science and physics from University of Science and Technology of China, respectively. Now let's start with today's seminar and welcome Junyuan to give his talk.
Okay, thank you. I will start my it's very honor to present our work efficient split mix federated learning for on-demand and in-situ customization. This is a collaborative work with Hao Tao, Zhang Yang, and Jia Yu. So let's start from the our work is like originated from the inherent trade-off in deep neural networks. That is, when a network is efficient, which cannot be simultaneously accurate. During the training, you will choose the size of the model. Here we define the model size as the Ys. For example, the number of channels in each layer. So you will have to choose a size of the model during training, then you will get a specific size of model. When you choose a smaller model, it will be quite efficient in for inference, but it may not be accurate. But if you want a model to be accurate, it usually should be larger one, and here is to be wider one. Similarly, we will observe another trade-off in the robustness and accuracy. That is, when you introduce like adversarial training to regularize the model, the harder you regularize the model, you will get a more robust model, more robust result. However, this model may not be that accurate on standard images. So this kind of trade-off cannot be simply reconciled in a single model. So in practice, when a client want to train a model, it will train one by specifying the parameters in advance. For example, a mobile phone will get a model by specifying a full Ys model. Here we assume this model is of size of Ys 1%, 100%. And meanwhile, it may assume this model to be non-robust by specifying the lambda to be 0. Therefore, we'll get a constant or static local model for this device. However, in practice, at runtime, the requirement of this client may not be constant. That means the mobile phone may be sometimes quite low in memory, like when you run multiple applications simultaneously. And at this time, this device may require this model to be a smaller one, such that it can inference efficiently. Meanwhile, it may want this model to be more sensitive to be more robust, because this device may enter some security sensitive environments. So it will change its requirement for this model. However, because of this model is totally static, we cannot change it. So we cannot use this local model to satisfy this requirement. Instead, we may design another model somewhere else. So find such a goal, one straightforward solution is that we can ask a cloud to train multiple models at the same place. That is, you can train models with different parameters and stored in a model zone. And for example, you can use like Amazon Cloud and to train this model and store it. Whenever you need a specific model, you can request a new model from cloud and download to satisfy this requirement. Although this is the plausible way and you can leverage the powerful computation resources in the cloud. However, we still think this method is of some flaws. For example, there will be a very high cost even for a cloud to train multiple models, especially when the requirements become like high granularity. So the storing this large value of models in the cloud is not efficient. It's very costful. And for a client, you have to request every new model when you have a new requirement. That's quite inefficient in switching or storing these models and even downloading these models. So this is obviously not a good idea. So recent trend in the machine learning that people introduce a method called customizable models. It allows model to be customized on device. That is, you can train a single model on a cloud and download this model to your device. For example, your mobile phone. You not that you only need one model and store one model locally. Then whenever you need a different model with different parameters, you just do in-situ transformation of this model. For example, you can drop some parameters in this network in a specific way, and therefore you can get a smaller network which can efficiently predict. And similarly for robustness, you can switch a few parameters in this network to gain better robustness. So this method was published like 2019 ICRR, and the first one is called the streamable network, which allows you to train one model, get different device simultaneously. So the blue line is like individually trained different models, and which is like very costful. Like the red lines are the mobile. The red dots are the individually trained models, and which is costly, and the blue dots and transformed from a single model that you will only simply remove some parameters to reduce the model size. So this is a very convenient method that where one model provides different variants on demand. Later, like in 2020, another work proposed the once for all those through training that allows you to do the similar trade-off between the standard accuracy on clean images and the robust accuracy on those images. So the red points are like individually trained multiple models. You have like when your model is more robust with higher robust accuracy, your standard accuracy will be a bit lower. And the green line is like customized by few parameter changing. So this customization will be efficiently done and allow you to achieve similar trade-off between like robustness and accuracy. So this is a current solution for model customization. So the key question is how can we train this model? Even this solution kind of very efficient in storage and efficient in on-demand switching. The problem is how can we train this? One traditional idea is that if we have consideration in practice that we have to collect some data from users and then we train a model. So the point that we have to first collect a large value of data from like multiple devices like mobile phones or whatever devices you can get in touch with. Collect all their data to a central server in this central server, you can apply like the traditional idea called streamable learning to train different subnetworks simultaneously. The technique called the technical streamable learning will like whenever you want like a customization at test time, then you do the training of customization during training time. That is, you will, if you want this subnetwork to be effective at test time, then you train this subnetwork during training. So each subnetwork is defined by a smaller width of a network, which means a subset of channels per layer. And we will define this model size in a similar way. We will define the width and the subnetwork by like a 0.25% of this model. This is like 1/4 of this model, which will greatly reduce the parameters like by 1/8, right? So this is the traditional way to do to make a model customizable at test time. So, but what's the problem with this method in practice? The first problem is like the privacy. When you collect all the data to the central server, you will like you cannot guarantee the privacy. Probably the server will be attacked by a hacker, and you may leak information to any malicious hacker. And meanwhile, this strategy is prohibited in many countries' laws. For example, in Europe, data collection to the server for a different purpose is not allowed, unless it's authorized by the user, but usually it's not. So privacy is a big concern in practice. You cannot simply collect all the data into a server. A second concern is that collecting all data to the server could be a burden for a client, because you have to transmit a lot of data that may be not efficient for small devices like mobile phones. It usually will need network for many tasks, but not for like training a less relevant model. So communication efficiency and the privacy is a big issue for this central customizable learning. A very good alternative could be federated learning, which is very popular recently, which will respect the privacy and benefit the communication efficiency. The key idea is that we will not upload all the data to the cloud. Instead, we will like allow the model to train a local model. Allow the client to train a local model using the local data without any sharing. The benefit is that first, obviously, when you don't share the data, then you are less likely to leak your personal information. And meanwhile, because you don't upload the data, you can save a lot in communication. Like you only need to upload the models, and to further reduce the communication cost, federated learning will allow you to like periodically uploading models, and for several epochs, and then upload. Then this will be very low frequency, in very low frequency, and you will see that you will no need to like transmit a lot of data. So this is the background in the federated learning. So the question is, can we like simply combine these two ideas to train a customizable models? Like we can do the streamable learning locally and upload the model to the server. Then we download a customizable model for a client later. So it's possible actually. When you do the streamable training, you can aggregate whenever you train the models to a cloud, and the cloud will simply, for example, by FedRBN, it will simply average the parameters into a new model by aggregating uploading the model from multiple clients. This aggregation is agnostic to the local training paradigm, so it's totally fine. You can use any learning algorithm, including the streamable learning locally, to do your training, and then therefore the combination is possible and it should work. However, reality is not this simple. Federated learning includes so many clients. The clients could be highly heterogeneous, and there will be new challenges when you apply this framework in reality. The challenge in reality is two phases. First one is the device heterogeneity. Just like we consider the hardware conditions for test time for which we want to do a customization. Similarly, in the training, we will see that the device will be of highly heterogeneous. For example, in this federated learning, we have different devices given by different nodes. For the level, maybe we have some devices like cloud AI, which will be allowed to you to, there will be many GPUs. You can do very computation intensive tasks. Like you can have like a very large memory. You can do computation very quickly, and you can also transmit a lot of data. And then you even no need to worry about how much energy you consume. So this is a very strong device, and you can do a lot of things. However, in comparison, there are also many other devices which cannot afford this similar tasks because they only have very low memory, low computation power, and even they cannot transfer too much data. And most of us, we have to consider energy consumption. For example, for a mobile phone, you may not want your mobile phone to be like drawn by this training. Therefore, so many data will be mixed in the federated framework. We have to consider how can we handle this different devices. So the different devices will bring in changes in running time, the transmission time, and the memory and energy capacity. Yeah, and meanwhile, we have to consider when you use a mobile phone, you will worry about what kind of model I can run. I don't want to run a very large model, so we have to consider the inference efficiency. So this is the device heterogeneity, and so since some devices is not that powerful, our question maybe can we simply drop this low resources devices and then just do training on these powerful models, powerful devices? Practically it's possible, you can do this, but the problem is that the model may not performs well because the devices may collect data from different data distribution. Some devices may collect the clip art. Some devices may collect painting images or real images or sketch. Different devices collect so different data. When you only train a model on a few devices, it's not likely that a model will generalize to other devices. This challenge is called the feature heterogeneity, because when different data have different images, they have different features, and they have to carefully handled by this model. So with these two challenges, so our question become, how can we train a customizable model that are affordable? I mean, the training are affordable by all devices, and the final model is adaptable to all local features. So in this talk, in this work, we provide a novel solution called split mixed federated learning, which will achieve this goal by a split mixing strategy that will fit this federated learning algorithm to all devices. Therefore, we can learn all features, and most importantly, it will output a customizable model that can be efficiently switch between according to client's requirements. So how can we do that? So before we introduce the details, we have to take a close look at the challenges of the current model size customizations. How the naive baselines work in this condition. So we consider two baselines. One is the federated average. In this case, we do not consider the constraint of device heterogeneity. We assume that we only train a single model wise and aggregate all parameters. We just want to know what's the ideal upper bound for the performance. And hetero FRO is a recent work which allow adaptive model voices by streamable learning and aggregates trained subnetworks accordingly. So this is, you can treat this as a simple combination of the streamable learning, which is a very advanced customizable learning, and with the federated average. So we to introduce the device heterogeneity in the federated learning, we limit the affordable model voices by different kinds. We assume that 100% of the clients will afford like the smallest network, and we gradually reduce the clients for each the client number for each model wise. And for the largest model, we only allow like 1/4 of clients to afford this model. So we can easily see that this, as a result, that different model sets will be trained by different number of data, because it will be limited by the devices. So here we visualize some comparison of the customization directly. That the blue line is the x-axis is the model wise. Like we consider 4 kind of model wise from the smallest one to the full size model, and the y-axis is the accuracy we achieve during the training. The blue line is an ideal upper bound that we allow the FedRBN to do full size training on all kinds. Therefore, this is a very very ideal condition, and it's not achievable in practice actually. So and we want to approach this by like customizable learning, and we see that this dashed line is the effective customization by our method. So we will introduce the method details later, but we just want to see that how well this will performance. And we also want to highlight that the baselines may not provide very good customization. The problem is that, for example, the red dash lines, although they can customize the model size, but the accuracy is not so good, especially for a large model. It will use more parameters. It will be very inefficient, but it's not accurate. This is like totally against the purpose of customization. Customization means larger model, better accuracy, but this is not. So this is quite an ineffective customization. So what we want is an effective customization that provides better accuracy when you gain more parameters. So what's the problem here? Why the traditional method will fail here? So we further take a look into the training process. We check the validation accuracy during the FedRBN. We see that the dashed line is the streamable, like the FedRBN, the customizable learning baseline, and the solid line is like the individually trained FedRBN, where we will ignore the constraint of the device heterogeneity. We see that even the dashed lines will, like the full size network will have converged to some point with much lower accuracy, even compared to smaller network. And we further see that this full size network is even worse than a smaller network by like training on all data. And we noticed the only difference between like the small network and the large customized model is that they are trained in different size of data. We can easily find a list in this table that the full size network in the customizable learning is only trained in 12.5% of all clients. That means since we uniformly split the data, so it's only 12.5% of the whole data set. This is a very small subset of data, and we also noticed that this results in almost 75% of the used parameters are not trained, are not well trained. They only seeing this small subset of data. This is a big problem. why this happens? Because if we can take look into a layer of the network, the weight matrix of one layer is like we can visualize it as a square matrix, and streamable learning will like gradually train different sides of network depending on the wise. So the smallest wise will have the smallest matrix, and the full-size network is the dark green. They will share parameters in some parameters in some points. So streamable training in federated learning will like download a subset of parameters to the client and train it, and it can totally not train the dark green part because this part has to be a full-size network, and it can totally not fit into a client with constrained memory. So we will see that this is like 75% of parameters because they are not trained, so they do not generalize well. This is very, very reasonable. So observing this problem, we propose a null method superior mix. Our intuition is that we want to make all use the parameters to be trained. Yeah. So since the traditional structure of the streamable learning use the full-size network, I mean that means all the parameters in the matrix, so it always cannot fit into the client. So our point is that our idea is that we will restructure the model to more affordable subnetworks. That is, given the same metrics, we will not get subnetworks in the streamable way. Instead, we will like split the network into different subnetworks independently. Without you can see that we have different subnetwork with the smallest matrix here without any interaction with other subnetworks. So we can extract this subnetwork independently into multiple ones, and we will find that each subnetwork is small enough to be universally affordable by all clients. So because each subnet is affordable by all clients, that means we can train all the parameters by all clients. But it's still not very clear how can we this is like still a lot of parameters, and could be a full-wise network, and that means you still have to consume a lot of memory in each layer. You have to store the same size of features per layer. So the problem is how can we train that? So the trick is that although each device can only train a finite wise of the network, we can train these subnetworks in different time points. Like at round t, we will train a local network or by two subnetworks here, and at the next time we will train another two subnetworks. This is totally like a random selected, and in a global view, we will see that the subnetwork will be all the parameters in the subnetwork will be trained by all clients, even though it's not in one round, but during the whole time sequence, you will see that all parameters will be trained. So therefore, we address this problem that traditional method cannot train all parameters, but now we can train all parameters, and by splitting the network in a different way. So the following question is, how can we mix them back into desired network size? So the mixture is pretty simple. We just using an ensemble strategy. That means we'll given different subnetworks, will combine the output by of them and average them to get the final prediction. This can be efficiently done, and at that time, and you can freely choose what kind of networks you want. So So to further understand why this simple strategy of mixing can provide a good performance compared to like a full network. The key point is that the subnetworks already such that subnetworks are like has less parameters, but actually they provide more diverse features. So this is reviewed by the 2020 paper from Aaron Zhu. That they show that the different network using ensemble can get different views or different features by different subnetworks. So here we also visualize the features by the gradient saliency. We will see that the 6 different networks will pay attention to quite different features. This the first image is the first subnet will like pay attention to the center part of the laser, and this one will pay attention to more to the root of the laser. Similarly, different models will provide different feature attention. Therefore, combining them will naturally provide better features, and finally we will be able to predict more accurately based on like more diverse features. So in summary, our method is like included two parts. One is the split the network into like 8 different subnetwork networks independently, like by a novel way compared to the simple learning. Then which allows we to train this subnetwork and all parameters of the full size network adaptively on all clients. And this kind of design also allow us to mix this model afterwards. That we can, depending what size you want, you can choose how many subnetworks to ensemble into a larger network. Yeah. So this is such sphere mix, the main method, and this is the experimental results for model customization. We experiment on 3 datasets, the CIFAR10 with non-ID class distributions. Each client will like have a subset of classes, 5 classes each client, and they are totally randomly selected clients. So in this experiment, we show that our model can like when we increase the model wise, our method has better accuracy compared to smaller network, while the baseline will like gradually reduce the or barely increase the accuracy by introducing more parameters. And this REST network, we will show that this network will like will take a very small size of memory to store this model, and it's very efficient in computation in terms of the multiplication and addition counts. So in practice, you can see that this model can be totally fit into in a small device like just a Nano or Sony's intelligence device that's which can only afford 8 megabyte networks, and even smaller network you can use it in like even smaller devices like the tiny sensors. So similarly, we also extend the experiment to other feature non-ID federated learning. By feature non-ID federated learning, we mean that, as we showed before, that different clients have different feature distributions. Some devices may use the MNIST, and some devices may use the street view digital numbers as the images. And then we can see that the heterogeneous FML, like they may train a good small network, but their larger model is totally useless. And this is not an effective customization. And especially in the domain net, which is like a larger data set with a larger image, and it's quite hard for recognition. And in this task, we show that this task will introduce a very much larger feature difference because the different domains will like have a very large domain gap, and it's very hard to for you to for a model to transfer from one domain to another domain. Therefore, in this case, we will see that our advantage is like enlarged compared to the hetero baseline. We basically achieve the accuracy even better than the individually trained models on all model sizes, and the much smaller model parameters compared to the like hetero. Yeah. So this is a customization of model size. Here we also provide some qualitative study to show why our method works so well, especially on the domain net, which will suffer from very high feature heterogeneity. In the first figure, we show that the percentage of trained parameters is like almost always 100% for our split mix method, and similarly for the Fed average. Because for Fed average, we assume that we only like we will train the full size model, we ignoring the device heterogeneity constraint. And in comparison, we will see that the FedRBN does not have this advantage. That in the first domain, they barely train parameters, so it's no wonder why they will fail in this domain. Their failure can be verified in the right two figures. That we compare, we compute the accuracy drop in each domain with respect to the fully trained network. Because in the clip-out domain, split let's say hetero do not a lot of parameters are not trained in this domain. So we can see that the full size network suffers from a 22% accuracy drop. And then comparison, our method barely drop in all domains. We perform so well on all domains compared to the ideal upper bound. Yeah. So this is a perspective to understand why our method works so well. And in addition, we extend our work, our split mix idea to robustness. Based on Cihan's work in 2019, they revealed that the network should be split into two branches per layer. In each batchization layer, you need to use two batchizations separately for two different tasks. One is for the claim prediction on claim data, and another one is for the noise data during training. So this split will do adversarial training through forwarding data by the noise batchization, and another one, if your input is clean, then you will go through another branch. So this is the trend. This is the previous insight to how can we make the model performs better, both in clean and adversarial data. And in our work, we simply modify this. So this is already the previous idea in splitting the network. Now our contribution is on how can we combine them back. We provide a embarrassingly simple method. That is, we only combine the output per layer of the batchization by linear combination. That is, if we assuming we want to customize this model by a parameter lambda to trade off the robust accuracy and the clean accuracy, then we will use this lambda as the weight in the linear combination per batchization layer. So we do not need to modify anything in the training. We just need to do this mixing at a test time. Then we will get the trade-off between the accuracy and robustness. And because this method is pretty simple, we can also make this work with our previous model size customization. So this is the experimental results that we when we co-customization of the model size and the robustness on the CIFAR10 dataset and the dominated dataset. In the CIFAR10 dataset, we can see that this customization will provide a better trade-off depending on the model size. When you have a larger model, you will get a better trade-off. And this is compared to like the federated average with like individually trained by those training. Yeah. So similarly, result can be observed in a more complicated and larger image size. Like a dominator will have like a larger image size, and in this task, we will see that the gain of the robustness is much larger in the large model. So in summary, in this work we provide the first insight into the failure of the traditional customizable learning together with the federated learning. We show that the device heterogeneity will hinder the parameter training because some devices cannot afford the training. Then the parameter, a lot of parameters will not be trained and they will not generalize well. Therefore, we introduced a novel split mixed federated learning approach for training models that can be customizable both on size and the robustness. Our method provides like the most efficient and accurate customization in non-ID federated learning. We also summarize a table that shows even compared to several naive baselines, that means we will apply traditional ideas into federated learning. Our method can not only customize the training in terms of size and robustness, but also customize the inference at test time. And most importantly, provide very accurate and large models that makes this customization very effective. Beyond this work, our other works also consider more training customizations in heterogeneous federated learning. For example, in the FedRBN, we relax a subset of the clients from the adversarial training. To mitigate the robustness loss, we let these clients to gain robustness from efficiently gain robustness from other adversarial trained clients. And more recently work, we extended the split mixed problem setting to resilient federated learning. Well, this federated learning may suffer from poor communication conditions. For example, the model transmission may be lost, some parameters will be missing when you upload or downloading models. So we provide a progressive learning strategy to make this federated learning robust against this noise. Yeah. Okay. Thank you very much for listening to my talk. This is our paper, and you can find our code online. Yeah.
Yeah, thanks Junyuan for the great talk, and I think it's very interesting and very insightful. So is there any questions from our audience? So if you have any questions, please feel free to open your mic or just input your question into the chat box, and we will answer it later. So maybe I have several questions first. So could you go back to the page 25? I have several questions for here.
Okay.
25. Yeah. May I know how to find the 75% parameters in the network? I mean, how to measure whether the parameter were trained or not trained by some specific data?
Yeah. So first, this is by the problem setting. We assume only 12.5% of clients can afford the full size network, right? So yeah. So that means most parameters will be trained by other clients, but there are some parameters are not trained, right? So well, we can take a look at the one layer of the network. That is we have a weight matrix, which is a square. And we can see that this part of parameters should be trained, and we assume this is the one like a half wise of the network. Then we will see that the rest part of the parameters are not trained because this is the full size network. They only be trained in this clients, right?
Yeah.
So we know that this part network is like half wise.
Yes.
So the number of parameters should be 1/4 of all parameters because it's the square, right?
Yes.
Yeah, the wise is this is the wise. So the area is like the 1/4 if the wise is the 1/2. So the rest part of the parameters should be like a 75% by subtracting the trained parameters. So yeah, so now we know that these parameters will not be trained by rest clients, so they only be trained on the like 12.5% of the data.
I see. Yes.
Yeah.
Okay. The second question is that from my view, I think the split method you can control which part of the model parameter to train by the specific data. So could we customize the client-wise device to use some specific parameter to inference some data from the client-wide? I mean, in the inference time, could we control the model to just use some specific part of the network to do the inference?
So what's the difference? I mean, the specific part. I'm not very clear about what do you mean by specific part of the network? So at the inference time, actually, we were like, if you want a half wise of the network, you will like select two sub networks to ensemble a large a single model, right? So what do you mean by specific part of the network parameters?
In other words, maybe I can change my questions. Do you think there exists some network is better than the deployed network, original deployed network in the device client for the for some local data? Since
okay,
the test distribution in each local client is sometimes different from the training data distribution.
Okay, I see. Yeah, that's a very good point, and I think there's already some existing work to consider this problem. Let me first summarize your question. You mean that for each client we may not follow the instruction of customization. We may choose some personalized subnetwork.
Yes.
That would work better than using, whatever larger model, right?
Yes.
So this is first. Of course, it should work. Yeah, and I think let's two sub questions. First, is there a better subnetwork to fit each client? Yes. There should be a good subnetwork from a large model that works better than large model in a specific client. This should be called the lottery ticket. I mean,
yes,
you should know it, right? Jonathan summarized that you can always find a subnetwork to works better than the original network given a specific data set. And the second question is that how is this idea, if this idea can work on the FedRBN, can we find a different lottery ticket or subnetwork specified for each client? Yeah, I think the answer should be yes. Yeah, actually, in the 2021, there's already a work called the Federated Lottery Ticket, and by Anli from Duke University. Yeah, they do exactly what you asked. They during the training in each condition round, they will tailor the global model by lottery, like the magnitude pruning to lottery ticket for each client, and then locally they only train this ticket and upload this ticket to a cloud, and they show that this totally work and especially good for non-ID federated learning. And yeah, you can, if you need, I can send you the paper later. Yeah.
Okay, thank you very much.
Yeah.
My last question is about the FedRBN, since I also conduct some research about adversarial robustness. So it means that it allows some device that cannot afford adversarial training can borrow the adversarial robustness from some computational capacity powerful client,
Devices.
right?
Yeah.
So if there not exist any clients that can afford adversarial training, just only a center model in the server is adversarial robust model. So can it also transfer the batch normalization layer from the center model to some client models?
Yeah,
Is
yeah,
it also
first
okay
question.
for FedRBN to do that?
Yes, but here I want to ask a question first. So how do you get a robust model in a server center server? Do you have an auxiliary dataset for training or what? But unless how do you get that?
Maybe
Yeah,
it's maybe it's a pre-trained model.
Yeah, okay,
So
pre-training model from a different dataset, right?
yes.
Okay. Yeah, I think there are actually you can directly recent just like a few months ago, there's a paper called adversarial pre-training. Like you can do contrast learning to train a model quite robust without using labels, without using downstream data set. You can pre-train a model, and you can fine-tune the linear layer, maintaining the robustness. So this is one way you can do that. You can do the robust pre-training with efficient fine-tuning. This is possible. So I guess here your problem is more specific. If we can train a robust model in a server, and which we will do end-to-end fine-tuning, because in that paper they only consider linear fine-tuning, because we know that if you do linear fine-tuning, you are very likely to maintain a robustness. So this is a good point, but in many times we want to do end-to-end fine-tuning, especially for FedRBN, we will do end-to-end training. So probably you may not maintain this robustness if you do the full network fine-tuning. And we also have some trial that if we can how many layers we can maintain the robustness. Actually, when the more layer you fine-tune, actually you will lose more robustness. And if we assume that you have an auxiliary density in the cloud, and for probably not distributionally similar to the clients, you can also leverage the idea of FedRBN to transfer the robustness from one domain to another domain. Because in this case, you can simply treat the server as a special client. I mean, you just do some training there, right?
Yeah, I see.
FedRBN totally work. And I think it's a very good idea if you we can try some other way to do that, except the FedRBN. Like I remember your work those role distillation. Like you can transfer the robustness from a teacher to students, right? Your previous work. Yeah, maybe you can combine that into the FedRBN. In server, we have a robust teacher. We can teach the clients how to do the robust training without using client's data.
Yeah, I think it's very challenging that if you want to maintain the robustness on one distribution to another distribution, like different classification task. So I'm very interested that FedRBN can transfer the robustness from one distribution to another distribution. Since I focused that I found that some experiments in FedRBN is on the domain net, right? So different client maybe the data on different client is not from the same distribution. I think it's very interesting that the batch normalization layers can provide such a characteristic to for this challenging task.
Yeah. So yeah. I think this is a very interesting point of the FedRBN, and we actually also wondering how can we like transfer robustness across domain, and the recent like today we just released a new version of the FedRBN, and we provide a new insight how can we train this robustness just through patronization. So I can quickly to discuss this. So the point actually we provide a very simple method called the shoulder noise calibration loss. So consider that we have a client which cannot afford those training. So but it can borrow some robust patronization from another client who is doing those training. So the key point is that you should fix this robust patronization when you do the local training, but you will also use clean data to train together with new patronization. So with this new patronization, this will place a low similar to the adversarial loss. Yes. Even though we have no need to generate adversarial samples, because this one is already trained robustly. So with this, we can transfer robustness from one domain to another domain. So, but to be specific, this transfer requires you to simultaneously train on two different domains. You can, I ever tried. You cannot train do this without do those training on another client. You have to do them together. Then you can transfer robustness without any of those samples. Yeah.
Okay.
You can check out the new version of our archive paper. Yeah.
Yeah, I will check it later. Thank you very much for the short discussion. Is there any question from our audience? If no, maybe I will start recording.